So usually we do care about the name and the type and the value. Not so much the address, because we don't assign the address. The computer picks the address. We don't tell it that, oh, you're supposed to store this name in address 2,300,005. So we could have a variable named operand 1. It could be of type integer, and it could be a value of 29. How do we know that it's going to be an integer? Well, in this case, they made the value a whole number, and that gives us a clue. Here's another one called result. It's a floating point, so it has a decimal. And then this one is a character. I would have put little single quotes around that letter, right? Because that's how you mark a character in this language. So like you can have, an int age is equal to 32. We don't really know the memory address, but we know the name of the variable. So the name is age, the type of it is an int, and the value is 32. The address, who cares? We don't care. These are the 3 things that are important to us right now. Say we declare another variable, right? Wait. We didn't initialize, I don't know why I'm making everything a comment. This is just a notepad file, right? We didn't initialize wait. We didn't give it a value. So its value is undefined. Now it may really have a value. If we printed it out, it might have some kind of random number in it, but it's not a number that you can trust. Initializing a value is if you do something like that. That's called initializing it. All right, so the name of this one is wait. Its type is int. Its value is uninitialized, undefined. Yep. Every variable has to have a value before we can use it. And again, its address is a who cares. Like if I did this, int y is equal to wait times age, for whatever reason, this is an error because wait is undefined. Well, it's not undefined, but it's uninitialized. Undefined means that we don't even have a variable of that name. Like if we do int z is equal to age times, I don't know, x, we never defined an x variable. So x is undefined. That's a definite syntax error. We might get away with compiling this. It might give us a warning that's saying it's uninitialized, or it might just flat out not work. It might give us a syntax error. Either way, it's a big problem in the making. Let's play with that. Let's go ahead and create our new project. See if we can use an uninitialized variable. See if it'll count it as a syntax, an error, and won't compile, or if it'll compile and it just doesn't do much good. So I'm going to do file new, empty project, C underscore lecture E. I'm putting the C underscore just because I also teach C++ and I have to have some way of distinguishing the two. You don't have to do that. Make sure it's in a good directory. I like storing my files in the documents directory. So I chose browse, went to my documents directory. Click OK. Now I need my C boilerplate. I'm going to go and find my C boilerplate. Alright, this is my newest version of the C boilerplate. If you don't have all of these things, like you may not have that line, I finally found that line, then you might want to add it. So I'm just going to copy the whole thing, paste it into here. Whoops, I haven't even made a file yet. I'm supposed to have the visual, the Explorer over here, Solution Explorer, and I don't, so I'm going to choose View Solution Explorer. That'll pop that up. Source files, right click, add new item. Source.cpp is a little bit too generic, so why don't I call this lecture e.cpp. Alright, now I can paste my boilerplate. I shouldn't have called it .cpp. I should have just called it C. But C++ is backwards compatible with C, so it's okay to do that. All right, I'm going to compile it to make sure it works. All right, it worked. This is here to stop it from this warning from causing it to crash, well, causing the compilation to stop if we are compiling it under what's known as the new GNU C compiler, GCC. Now, we're not using GCC, we're using Microsoft Visual Studio, so this line is not important. However, I want it there so that we don't have to correct it later when we're using the GCC compiler. All right, let's try int age, and let's print out age. Printf, parentheses, quote, age equals %d \n, end quote, comma, age. See if it gives us a warning or what. Uninitialized variable, and it did count it as an error. We could probably disable that error with a disable message. Don't do this, but as an exploration, I'm going to try disabling that error. Tell it to ignore that error. I wonder if it'll work. I wonder if it'll compile. It did. And then boom, it blows up. The variable age is being used without being initialized. So it did crash. That's why it's a good thing that that error is treated, that warning is treated as an error. Can I delete that line there? There we go. So there are lots of different data types. Pretty sure we talked about this page. The difference between a short and an unsigned short is that an unsigned variable can't go negative, so on the positive side it can go twice as positive side of things, it can go twice as high. Just like a long and an unsigned long. A long can hold a unsigned long can hold twice as much as a long because unsigned means positive only. And then there's a type called a long long, which holds more than an unsigned long. Holds a huge number, 9 gazillion. So constants and variables. A constant is a number that once declared can't be changed. Primary constants are these data types. Secondary constants are these data types. Don't care about that. So an integer constant must have at least one digit, and it can't contain a decimal point because it's an integer. It could have a plus or a minus sign in it to indicate whether it's positive or negative. Commas, blanks, and non-digit characters are not allowed in integer constants. So if we did age is equal to, I'm really old, 2000, 170. That's a syntax error because there's a comma in it. That's not going to work. If I put the word constant in front of it, then it can't change later. If I try to add one to it, age plus plus, taking one and adding it to age and storing it back in itself, it's going to say that age is a constant, and so it's not legal if we look at the error list. Not sure why it's not showing the error list here, but if I build it, whoops. Whenever you're in this state where there is no build option, you need to either find the app down here and kill it, or you can just press the little red stop debugging message, get it to stop. All right, now when I try to compile it, it's going to complain. It needs an L value. Well, that's pretty cryptic. But above that one is expression must have a modifiable L value. Well, what's an L value? It just means one on the left-hand side of the expression. If you have this, age is equal to 10, this is the L value, and this is the R value. And if L value is a constant, then it can't be changed. So why do you declare constants? You declare constants just to stop yourself from making mistakes. If you declare your variable as a constant, then later on down in the code, if you try to change it and it shouldn't be changed, then it'll give a compilation error. Or if you're working with a team of programmers and it better be something they don't change, then you go ahead and make it a constant, and that gives them a clue that they shouldn't change its value. So I'm going to delete those 2 lines since those are syntax errors. And the value of an integer constant cannot exceed the specified limit. So if I went back here and saw the limit of an int, which is about 2 billion, and tried to store a larger value in it, right, more than 2 billion, let's make this on my age is 3 trillion, so I'm going to need 12 zeros, or even 3 billion would do it, so that's 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. And it worked, but it came up with a negative number. So it was too large. That value was too large to store into an integer. What if we made it trillion? What would it do then? Still doesn't work. It's a positive number again, but that's only 2 billion, right? So it needed to be 2 billion or less for it to successfully work. We're going to go back to saying I'm a youngster. My age is 20. So then there are real values. Floating point and real are considered interchangeable numbers. Real is just a math term. We're going to call them floating point numbers. It's something with a decimal. You can represent a real number, a floating point, either in decimal form with a decimal point or exponential form. So like Avogadro's number. Avogadro's number. If we're going to make it a float, we could say that it's equal to 6.022 exponent 23. Ooh, and it's giving me an error. Expected a semicolon. Well, there's a semicolon. Oh, I forgot the equal sign. That's just a term from physics or chemistry. We're not going to use it. I got an error. I mean a warning down here. Let's see if we can spot it. Truncation from double to float. Whenever you see the word float there, just go ahead and change it to double. A double is more precise. It has fewer rounding errors. It occupies 8 bytes rather than 4. Just as a matter of course, if you ever write code that has the word float in it, instead use the word double. It means double wide floating point. Now it's not going to have that warning when I try to compile it. Right. We're not printing it out, but you know, we could print it out and see what it equals. So in exponential form, it's got 2 parts. The first part is called a mantissa. And then this is the exponent. So let me put a space in there temporarily. 6.022 is the mantissa math term. 23 is the exponent. So what this means is 6.022 times 10 to the power of 23. That's what that means. That's all that scientific notation means. Or a 10 with 23 zeros after it. So this has about 23 zeros after it, whatever that is. So floating point numbers can be much larger than integers, because an integer is limited to 2 billion, like I said. Now a long, which is a long integer, a huge one, a double wide integer, can hold a lot more. But a float, since it has the exponent there, can get much larger, right? 6 with 23 zeros after it's much larger than 2 billion. However, it's not as precise. Why is that? Because it has to store both that part and that part. And so there's not as many pieces of information available to hold the mantissa as there are in an integer, because it has to save a lot of space for the exponent as well. So integer math is always exact as far as integers are going. If you take 3 and you add 1 to it, it's always 4. But if you take 0.1 and you add 0.1 to it, it may not equal exactly 0.2. And I don't remember if I gave you this example or not, but let's declare a double. I'm just going to call it D, and I'm going to assign it 0.1 as its value. Then I'm going to multiply by 10. And then I'm going to subtract it from 1, because 10 times 0.1 should equal 1. So that should be exactly 0. Let's find out if it is. So I could write it like this. D is equal to D times 10. That would do it. Or I could have just written D times equals 10. If you're a Python programmer, you may remember that syntax. Just means multiply D by 10 and store it back into D. All right, so 10 times 0.1 should equal 1. So we're going to say double D2 is equal to D minus 1. And we're going to print out D2. So D2 is going to be the difference between D and the value of 1, which should be 0, because D should equal 0 after that. So printf, parentheses, quote. This is a floating point number, so I can't print it out with %D. I need to print it out with %F. I'm going to just say rounding error equals, like that. And so after the comma, we're going to print out D2 because that's the rounding error. If it has one, we'll check it out. It might not have one. It doesn't look like it has a rounding error. What if we printed out more decimal places? What if we said it needs to have a decimal point followed by 30 zeros? Now that's too large. Not even a double can go out to 30 zeros. But okay, make a liar out of me. Alrighty, we're going to try something else. Instead of multiplying it by 10, we're going to add 0.1 to it 9 more times. So D plus equals 0.1, and I'm going to copy and paste that so that it adds it 8 more times. So that's adding 1 to it, adding twice, adding 3 times, adding 4, adding 5, adding 6, adding 7, adding 8, adding 9. Whoops. Is that enough? 1, 2, 3, 4, 5, 6, 7, 8, 9. One more time. So I should have 10 addings right now because I still want it to add up. Well, 9 addings because it started off as 1. Right? Started off as 1 and I want it to equal, it started off as 0.1 and I want to add 0.9 to it. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now get rid of that. Now let's see if there's any rounding error. And if it doesn't work this time, we're just going to give up. All right, there we see it. Right? It should have equaled 0. Instead, it's got all this garbage in it. That's a rounding error because floating point math is not exact. What do I mean by that? Math is supposed to be exact, right? Well, what if you had something like this? You're counting it in base 10, meaning our normal counting system. And so you want to represent 1 over 3 as a decimal number. Well, what is that? It's not 0.3. It's not 0.33, right? What it is it's an infinity of these. Right. Use up all 8 gigabytes of RAM on the computer typing 3s. It still wouldn't be precise enough. So what the computer does is it kind of rounds it off. And then when you start doing and you start adding math, if we added that to that to that, we would get 0.99999 and not 1. 1/3 plus 1/3 plus 1/3 should equal 1. But it doesn't in floating point math because it can't represent every number precisely. It just can't. So anything divided by 3, it can't represent. Anything divided by 7, it can't represent. The even numbers can pretty much be represented exactly in floating point. Now that's base 10. Base 2 would be able to handle anything that's a power of 2. It can represent 1 over 2 exactly, 1 over 4 exactly, 1 over 8, 1 over 16, but it's not going to be able to represent 1 over 9 or 0.1. You know, because that's 1 over 10. 0.1 is equal to 1 point. So you can get rounding errors with floating points. So if you want to check the value of a floating point and compare it to something, here's what you can't do. You can't do this. If D equals 0, print F D equals 0 \n. But that's not going to work because it doesn't equal 0. We've proven that it doesn't equal 0. It equals something a little bit off. So if I run it, I'm not going to see that message. Does not equal 0. So you have to check to see whether it's really close. I forget. Do we have the absolute value function? It's part of the math library. Did we include the math library up here? Okay. Yeah, so we might be able to get this to work. If the absolute value of D minus, how precise do we want it to be? Let's say out to 8 million, or 1/1,000,000th. So we're going to need a point followed by 6 zeros. 1, 2, 3, 4, 5, 6, like that. There is no absolute value function. Oh, that's because that wants integers. All right, I've forgotten the name of the floating point absolute value function, so let's find out. Double absolute value C. FABS. Okay, FABS. FABS. All right, floating absolute value. That just means, absolute value just means you drop the negative sign if it has one. So if the absolute value of our number, there's something I'm forgetting. Oh, I need to subtract it from 0 or from 1. It should have equaled 1 at this point. I think I botched it. I think I botched this example. I wanted it to equal 1. So it should have equaled 1 here. It didn't. So I need to rewrite that completely. I'm sorry for the mistake. See, this comparison, D should have equaled 1 at this point, but it didn't. So if, parentheses, FABS, parentheses, D minus 1, in parentheses, is less than 0.001, we don't need to go nuts with the zeros, then printf D is pretty close. I need to change that to D equals 1. Sorry for all the changes. I don't know why my brain glitched and thought D equaled 0 after we added all that to it. Okay, so we're going to printf D is pretty close to 1 \n, because it is. It's within 0.0001. Pretty close. Not exactly. So when you're doing floating point math, you're using doubles and floats. If you need to compare it to a number exactly, you're not going to be able to compare it to a number exactly. You just check to see if it's pretty close. That's kind of the rounding error. You know, it's pretty close to being 1, but it's not 1. So we had to do the subtraction and see if the difference between the two is within an acceptable error range. And we saw that our error is really pretty small, right? 0.000, that's a lot smaller than 0.01. So D is not exactly equal to 1, but it's pretty close to 1. So to compare a floating point value you should not use equal equal, because rounding errors might exist. Instead, compare it, take the absolute value of the variable minus the target and see if it's less than an acceptable error. In the example above, the target value was 1. And the acceptable error was this, 0.0001. That makes sense, gang? Good enough. All right. So a character. Why are they calling these constants? Just because this part is a constant. Nothing is going to magically go in and change that unless you edit it. So some people call them literals. They're literally put into your program, just like this number. Nothing's going to go in and magically change that unless I, the programmer, go in and change it. Same for all these. All right. Every number in here is a so-called unnamed constant, or a literal. That's a literal, that's a literal. All right. So we have constants that are floating point. We have constants that are integers. And now they're going to say that we have constants that are letters, like this. C-H-A-R-C equals single quote A. So if we were going to print out A, if we were going to print out C, we'd see just that letter. So in the code examples above, the numbers are so-called unnamed constants. So is that A, which behind the scenes is another number, right? An A, the computer can't store an A, but it can store a number that it pretends is A. The number that it stores in itself, we could find by going to ASCIItable.com, and if we looked, we'd find out that a lowercase a is equal to a 97. So if we tried to print out A, but we print it out as the wrong type, if we print it out as an integer, it would show us 97. Let's prove that now that I've talked all big about it. Printf, parentheses, quote, the ASCII value of single quote A in single quote is %d \n, end quote, comma, C. And we will see that it equals 97 as promised. Yep. And so if we printed out a lowercase b, it'd be a 98. If we printed out a lowercase c, it'd be a 99. Now usually if we have a letter, we really want to treat it as a letter. So there's another way of printing it. I believe it's %c to print out a character. Let's find out. Printf, quote, the character value is %c \n. And we could be putting spaces there to make it real clear what's going on. Comma C, but it's not necessary. End parentheses, semicolon. So it should say that the character value is lowercase a and that the ASCII value is 97. That ASCII meaning that it's got a numeric value that is saved in memory or written to disk, just because the computer has to have some way of representing it. I'm going to put single quotes around it just because otherwise it says the character value is a what? I guess we could change it, but anyways, I'm going to put single quotes around it like that. Make it look a little bit prettier. All right. So string constants. A string constant is a sequence of characters in double quotes, like this. Guess I better look at our example a little bit more before I scroll so quickly past it. Oh, they don't have an example of it. How sweet. All right, so we're going to do this. Char name square brace in square brace equals quote Bob in semicolon. Excuse me, in double quote in semicolon. Notice that since this is a string, it has to have double quotes around it. It doesn't look like a string. When I took Python, we used the word string. Well, by default, C++ does not come with strings. Maybe C++ does, but C does not. I may be wrong. We'll find that out in the PowerPoint. This defines a character array. What is an array? It's a list of values, right? If you took fundamentals of programming, or if you took scripting, you may remember the idea of lists. You could create a list of items and assign that a variable name. Well, here's a list of letters assigned to a variable name. Now there's a secret fourth character that we don't see. A \0 is hidden in there. And a \0 is called a null, because otherwise it doesn't know when the string ends. If we tried to print it out, it'd print a B, it'd print an O, and it'd print a B, and if there was no secret hidden marker that indicated that it was the end of the string, it'd just keep printing whatever in memory was after that. So that's called a null terminated string. There's a secret \0 null tacked on to the array to indicate that is the end of the data. So the length of this array is actually 4, not 0. So name is actually 4 characters, 4 bytes long. We just don't see the last one. We're going to use some print statements to print out the characters, just like we printed out A here and we found out that A was a 97. Tell you what, instead of Bob, let's make it ABC, because that'll be a real easy pattern to see. Maybe even capital it. There we go. So char name, square braces, this character array is equal to ABC. So, whoopsie, come back. Name is a so-called character array, and we call it a null terminated string because it's got some letters and it's terminated by a null. Let's prove it. Let's prove that it's terminated by null. We're going to print out 4 values. We're going to print out the first character, the second, the third, and the fourth. Maybe you remember that in an array, the first element is index 0, subscript 0, like an apartment complex, but the first apartment is 0, not 1. Then the second one is a 1, and the third one is a 2. So we're going to print those out. Printf, parentheses, quote, %d, %c, \n. We're going to print out the ASCII value of it, the numeric value of it, and then the character value. Let's even put an equal sign and single quotes around that, just to make it really pretty and all that. All right, we have 2 placeholders now. We need to fill in that placeholder and that placeholder. But in this case, we're just going to fill it in with the same value twice. Name subscript 0, comma, name subscript 0, because I want to find out the ASCII value at the first position and then the character value at that position. So I'm going to copy that and paste it and change the 0s to 1s and 2s and 3s and 1s and 2s and 3s. I need to check something. I apologize. I need to blip over to this just for a moment. I'm not seeing it now. Okay, forget it. All right, let's run it. We're going to find out what the 4 positions are. That's position 0, 1, 2, and 3, and the 4th one is the mystery character, the null. So if we run it, here we go. The first position is 65, the second one is 66, the third one is 67, and the 4th one is 0. Well, what do those values mean? Remember I said those are the ASCII values? We can go to ASCIItable.com and look up 65, 66, and 67 to see what they are. A 65 is an uppercase A 66 is an uppercase B, and a 67 is an uppercase C, and a 0 is a null. That's the terminator, marks the end of the string. I really need to find my example. Sorry. So we're going to change gears just so that we have something that we can play with for homework. So we're going to pretend this is a homework assignment. It's not, but sample homework could be this. Write a program that calculates a target heart rate. We need to know their age and the difficulty level, the exertion level. Now there's like a theoretical maximum, but if you're doing like cardio, you're not supposed to get to the maximum, or you fall over and you're unconscious or something. So you're like supposed to hit like 60% of your maximum, or 70 or 80. So we're going to ask them their age. So the formula is this: target heart rate, THR, or something like that. That's pretty. Target, how about that? That's a better word. Equals the difficulty times, parentheses, 220 minus age, in parentheses. That's how to calculate the target heart rate. So what are we going to do? We will ask the user for the age and difficulty, calculate the target, and display it. That's our goal. And I'm going to make all of these floating point values just so that we don't have to worry about the user saying that they want to type in that their age is 20.5 or something. And certainly the difficulty needs to be expressed as a fraction. It needs to be like 0.7 for 70% or 0.8 for 80%. We'll tell them that too. So let's declare our variables. Double age, comma, difficulty, comma, target. Now none of these are initialized, but that's because we're going to ask for the age and we're going to ask for the difficulty. I'm kidding. Okay, so let's ask for their age. Let's prompt them for their age. Printf parentheses quote. Let's calculate your target heart rate. \n. Or put a period there, but why don't we speak good grammar? Printf parentheses quote. What is your age? Question mark. And I'm real fond of using the greater than sign to tell them where to type. So greater than, end quote. Now, in all my printing, I have been putting a \n in there, but that goes to the next line, and I'm going to let them type on the same line as the message we just printed. So that's why I did not put a \n in there. Ooh.
So you wouldn't put printf, maybe you would scanf?
Nope, printf is great because we're displaying the message, but letting them type it in, we're going to need scanf. The syntax for scanf is a little bit weird. This isn't Python, so everything's slightly obtuse. So we're going to do scanf, parentheses, quote, %f, meaning that we're reading in a floating point number, end quote, comma, ampersand, age, because that's the variable that we want to let them fill in. And I'm sorry about the cryptic syntax. This lets the user fill in age with a floating point value. Let's just accept that that ampersand is necessary right now without actually explaining what it does. It's a voodoo at right now, but we'll explain it later. Okay, so at that point we know how old they are. Now we need to ask them for the difficulty level. So we need another printf statement. Printf parentheses quote difficulty. Okay, what is your target difficulty question mark \n in quote in parentheses semicolon. But let's tell them, let's give them a clue of what kind of values they might want. Like, you know, 0.5 is moderate, 0.75 is extreme, excessive, tough, strenuous. \n in parentheses, in quote in parentheses. Now let's give them one more message to tell them where to type it. Enter the difficulty, period, space, greater than, end quote, semicolon, or in parentheses, semicolon. Now again, we're going to need a scanf statement to let them do some input. So scanf, it's not scam, we're not doing a scam here. Scanf means input, let the user type in. We want them to type in a floating point number, so we're putting %f, just like we do in printf statements. End quote, comma, ampersand, and we called our variable difficulty. Don't know why I chose that, it's kind of a long word, but difficulty. So ampersand difficulty, in parentheses, in semicolon. Now we have those two pieces of data. We have asked for the age and the difficulty. Now we're going to calculate the target and display it. We have the formula here. I could just copy and paste it. But to slow things down, I'm going to go ahead and type in target equals difficulty asterisk parentheses 220 minus age in parentheses semicolon. Now we need to print the output. Again, I'm going to add a comment here. Let the user type input. That's what scanf does. Let's print the result. Printf, parentheses, quote, we have calculated your target heart rate, \n, end quote, semicolon. I'm going to remove the word have on mine just to make it all fit on one line. Printf as space % f space per minute, period, \n, end quote, comma, and then the variable we're trying to print out, which is target. Click run. I can't say that it did anything. I'm going to go and click my error list and see what it did wrong. All right, age is redefinition. All right, that's because we had age is equal to x way up there at the top. What are we going to do about that? Why don't we go and comment it out or something? Yeah, just comment those 2 lines out. Go to the very top of here, comment out that line, and comment out that line just to get it to compile. All right, I just saw another warning pop up. It may be a pretty minor warning, but let's take a look at it. Format string requires an argument of type float, but variadic argument 1 has type double. All right, so I need to find out what to put there for %f rather than a float. I mean, for a double. Let's find out. That's what Google's for. Scanf C example double. LF. Okay. Well, got to get funky then. Come back down to our scanf statements, and just to get rid of the warnings, it looks like it would have worked. It's a 4,000 level warning, meaning it's kind of a weak warning. But we want no error. So this looks like a number 1, but it's not. %LF. I wonder what would happen if I made that a capital L. If it would still work. Do the same with the other scanLF. That should get rid of our warnings. All right, good. Let's calculate your target heart rate. I'm going to make the font larger. And then I'll wander around because y'all may still have syntax errors. What is your age? Oh, I don't know. I'm old. I'm 80. What is your target difficulty? I may be 80, but I'm going to work out hard. So 0.75. All right. Calculating my target heart rate is 105. Now, I don't know if that's exactly right. Do we really need that many decimal points? Yeah, I think that's a little bit too precise. My Fitbit's not going to get out like that. So why don't we change our % statement just to display 2 decimal places? Even that's too much. But 2 is not, kind of nice. 0.11, something like that. So we're going to make this say %.2 on the very last statement of the code, except for that pause statement, which I think, no, we don't have a pause statement. Yeah, we do. Okay. So I just made that change. All right, I'm a young whippersnapper. I'm 20. I'm going to work out pretty lazy, 0.5. My target heart rate is 100. Okay, that's all looking good. Only 2 decimal places. I'm happier with my result. All right, I may need to check things out. I'm going to zoom out a little bit to try to get it all on the screen for the people looking at the video, because not everybody's here. And then you can pause it. Ooh, I'm having to get it small. All right. Pause the video. Then you can look it up. About this that we better make. Maybe I'll just put it at the bottom. Please note, I'm going to open a multi-line comment with a /*. We use printf, parentheses, quote, %f, end quote, in parentheses, to print floating point data. We use scanf, parentheses, quote, %f, end quote, comma. I guess I better put the comma and then the variable here, and so that I can do comma ampersand variable in parentheses to let the user enter data. Now, if they were going to type in an integer, you wouldn't put %f, you'd use %d. I'm going to change those to LFs just to get rid of those warnings. I better put a comment to that effect as well. use %f for float, comma, %lf, that's an L, for double. It just stands for long float. And since we're not ever going to use float, we always use double for accuracy. Our scanf should specify %lf. If we are printing, not printing, printing or scanning for an integer, use %d rather than %f. And if you don't want to type all that in, that's fine. You know I'm going to upload it. All right. So, homework based on this concept. 1. Write a program that calculates miles per hour, not pre-hour, per hour, by asking the user to enter the miles and the hours. The formula is MPH equals miles divided by hours. Make all variables double. And one of these isn't enough. So 2. I know. Alrighty. 2. Write a program that calculates BMI, which stands for body mass index, by asking the user their weight in pounds. You ever wonder why LB stands for pound? And their height in inches. The formula is BMI equals 703 times weight divided by, if you've got math.h, you ought to be able to do this, but I'm going to make absolutely sure. POW parentheses height star 2, which just means take your height and square it, close parentheses. Remember, you're going to have to put semicolons. Maybe I'll go and change that period to a semicolon and this one to a semicolon. Again, make all variables doubles. Use scanf in all cases to let the user type the data in. And just put that all in one program. You don't have to write 2 separate programs. And if you get stuck, text me for help. Not many people are texting me for help. Kind of leaving me lonely late at night. So. Alrighty. That makes sense, gang? 2 math problems? Alright, that's cool. Yeah, please do.
The assignment you gave me last week.
Uh-huh.
I did it, and you asked for a screenshot.
Yeah.
I took the screenshot, but the assignments folder won't let me submit the program and the screenshot. It'll let me submit one or the other.
Oh, that's weird. God, can you submit one, then turn around and submit the other one?
I tried to do that. It won't. It replaces one.
Get it bad.
Yeah, let's verify that. Let's make sure. I want to play with that. The question is how do we get both the screenshot and the program file? So I'm going to go into assignments. Well, I'm going to go into student mode. So
And I'm not even sure I submitted it to the right folder. I thought I did.
Well,
It was the integers and floating points homework?
yeah.
Okay.
So let's see. Student view, assignments. What's the number?
It was D,
It was D,
the top one.
chapter 2.
Oh, okay. So that's not the homework assignment. That's just the daily lecture. Not that that really matters, but I mean,
Well,
what I want y'all to do is after each day, upload your lecture notes if you made any.
okay, that I did, but
Okay.
where was I supposed to put the assignment?
Let's go look at the notes for that day. Modules. Lecture D. Well. Was it this one? The area of a circle?
No, it said write a program that creates a float variable and a double variable. And you wanted us to print out the size of the float and double using the size of formula.
Okay. I haven't spotted where that one is. Let's go to modules, homework assignments. Must not have been conversions using modulus. Was it first program?
I think so. That was something else.
All right, let's pause it and find it because